Today we're going to talk about an important application, especially for the more advanced wafer fabs, that can heavily leverage information in an EDA equipment model in a way that can improve the processing operation stability as well as yield of the eventual devices, while greatly increasing the efficiency of the software engineering staff in the factory side. So the application I'm talking about is lot completion estimation. And that's always been important because throughput of a factory is a key performance indicator. You want to build as much as you can without having material weight between process steps unnecessarily. But this is no longer just a productivity issue. It is now a yield issue in the advanced wafer fabs because some of the processes themselves will, the material will age or deteriorate if left exposed to sort of atmospheric conditions for more than a fixed threshold between process steps. And so it's important to know when something is going to finish so that you can schedule the material delivery systems to pick up that completed lot and move it on to the next process step in a timely way. Now, the way this has typically been handled to date is that the automation specs, the purchase specs for the equipment, will have a special section for the processes for which this is important that includes a list of variables and configurable event thresholds that estimate on a continuous basis how long it will be before the current lot is complete, and sometimes even until the tool is finished processing all of the lots that are scheduled for it. This allows the real-time dispatch software to schedule the material delivery systems to actually have carts available to pick up those lots and move them the instant that material is completed. Another feature of most of these interfaces is actually a configurable event, so that let's say at 3 minutes or 5 minutes or a 1 minute mark before a lot is complete, an event will be raised that will be sent to the control systems to say, hey, get this thing scheduled. And so the tool supplier, though, has been the one responsible for actually implementing this algorithm in their tool software because, again, it was part of the GEM interface spec for that equipment. Now, the difficulty with that is that once the tool is deployed, a lot of things can change. You can have new products, new recipes, new control techniques, and if you have to change the lot completion algorithm, then the chip factory has to contact the tool supplier to make those changes. A better approach, of course, would be if there was some way of using raw data from the equipment to actually calculate those completion estimates and generate those events without ongoing support from the tool maker. Well, the good news is that the EDA standards require fidelity of events and parameters and material movement information that support that lot completion algorithm completely. And so that way it can actually be developed once across a fab for the particular processes that are important, and just configured for each tool type. Now, the way that algorithm works, if you look at the E164 model for that piece of equipment, you'll see it's actually complex. It requires information from at least 3 of the software modules in the tool: the material manager module, then the job manager module, and the recipe execution part. And so you first have to consult the material manager to see what carrier is active. Then you use the material specs in that to go find the job specifications to see how many wafers are in each one of those and which recipe is being run. Then you go back to the material module and you see the actual motion of those wafers through the equipment, and you calculate the start to finish time for each wafer and update the average processing time continuously as that goes on. Since you know how many wafers are in the lot, you can extrapolate based on the average you've calculated so far and the number of wafers remaining. You can extrapolate the completion time for that point. And so this allows you to have a continuously updated estimate based on raw data from the equipment and no custom software on the toolmaker side whatsoever. And again, the other benefit is that since the E164 parameters that we're referring to are common to all equipment, they are not process specific at all, this algorithm could be developed that would apply for any tool type, and then just probably configured slightly with differences in recipe execution times for those individual tools. So you can see a way that the requirements of the EDA specs for the metadata model in the equipment actually supports a very advanced application that can be done in a way that is optimal for both the tool makers as well as the software engineering staff of the chip makers. So this presentation was excerpted from a presentation made at a recent APC conference in Europe, and feel free to click on the link at the end to get the rest of that material. So thank you.